Hi, everybody. My name is Edgar Dobriban. I'm Associate Professor of Statistics and Data Science at the University of Pennsylvania. Also have a secondary appointment in Computer and Information Science. And I'm very excited to be here and to host this webinar. So this webinar is part of a series that's organized with the help of the Committee of the Presidents of Statistical Sciences, the COPSS, as well as the National Institute of Statistical Sciences, the NISS. And these webinars basically are an opportunity to hear from leaders in statistics and related areas, learn from them, and ask them questions. So today, the topic is leadership in data science, machine learning, and AI. And we are very lucky to have two leading researchers in these areas. I'll talk about them in a second, Dr. Bin Yu and Dr. Arnaud Doucet. I will introduce them in a second. But to set the stage, so as we all know, we live in an era where artificial intelligence is gaining more and more attention. We have all heard about tools like ChatGPT or Diffusion. We have, perhaps even tried to generate code or images with these tools. And these techniques are based on fitting large models to data sets. So that's something that statisticians, we have been thinking about, at least, maybe smaller scale models, but we have been thinking about fitting models for a long time. And so it's really, an interesting question, an important question that our field, meaning statistics, should discuss of what should we do to stay relevant and make important contributions in this changing time. So again, I am incredibly grateful that we have two distinguished statisticians with us who have been successful in doing research in AI and really also in educational programs and industry work in this area. So I think we will all learn a lot from them. So I would like to first just mention a few things about our two speakers, panelists, and then I will hand it over to them to discuss a little bit about their own background and vision, and then we will do a question and answer session, and then the audience can, I will convey audience questions as well. So Dr. Bin Yu is Chancellor's distinguished professor and class of 1936 second chair at the University of California at Berkeley. She is also affiliated, in addition to the Department of Statistics, with the Department of EECS, Electrical Engineering and Computer Sciences. She has done a wide range of work in statistical methods, theory, as well as collaborative research with broad range of scientists, many areas. She has written incredible number of papers, hundreds of papers, tens of thousands of citations, as well as a topic that we will talk about recently written a book about veridical data science, exciting new directions. Her work has been recognized through many prizes and honors, including being a member of the National Academy of Science, American Academy of Art and Sciences, Guggenheim Fellow, Ward Memorial Lecturer, and so on. And she's also been serving the field extensively, including being president of the Institute of Mathematical Statistics, various editorial boards, committees, and so on. So we're very lucky to have her. Perhaps I would hand it over to her to hear a little bit about her own leadership journey and thoughts about where the field should be headed. So Bin, would you like to share your screen and talk about your leadership journey?
Thank you for the kind introduction. So I got a bunch of questions from Edgar, so I'm just going through them, and feel free to interrupt anytime. I probably have too many slides, so definitely feel free to stop me. So one question is like, how can statistics contribute in the age of AI? So I think my background, I started doing a thesis on theoretical statistical information theory, and at the beginning of empirical process and machine learning VC classes. But on the side, I read a lot about features, scientific problems, and tried to pick up the skills for applied statistics. But my thesis was completely theoretical, and over the years, I went into many areas: signal processing, information theory, remote sensing. My goal was, even for as a graduate student, was try to solve problems. So I was just gathering skills so that I could solve problems. And today, I think we are in an age of AI. And I think, how can we really engage in AI? We first have to understand how AI is done and in what culture. Most AI researchers are computer scientists and domain scientists. Domain scientists have been really fully engaged in AI, solve their problems. And they have large teamwork, usually multiple groups, even in academia, and with some shared goal, and they move very fast. Things happen, people finish paper in weeks, and the chatbots takes months for the new generation, like the Strawberry from OpenAI. I think a natural place for statisticians is actually trustworthiness and safety of AI, but there are gaps in the statistical community. Overall, I don't think we have enough coding skills to be competitive, and we're not used to working in large teams, and our pace is pretty slow. So what changes in statistics are needed? I think we need to define statistics broadly, expansively, and dynamically. And it's really going back to look at the age of Fisher. That's like 100 years ago. People really tried to solve problems. I think a winning goal of statistics is to really follow data science problems. We develop algorithms, relevant theory, and data science lifecycle in context solving domain problems. Many AI questions actually are more than statistical questions, so it's quite natural, I think, for us to engage if we define statistics more broadly. If we don't rally around this broad definition, I think we will have a lot more challenges coming our way. But most of our textbooks and our exams only cover a subset of modern statistical questions. So therefore, we're limiting ourselves, and many graduate students define statistics through what they learn in graduate school. I think changes need to happen, and fast. We really need to do reproducible, responsible coding practice in classes and in general data science life cycle. And we produce high quality software in Python and R. And I think deep learning should be taught alongside with linear and generalized linear models at every level of classes. It's just what people use these days. We need to move away this winner takes all kind of competition, mass competition mentality to have large teams working together on pressing domain problems. We should move faster while ensuring quality. The promotion should really take software as research product and seriously, and journals should have faster turnaround in weeks, and we need to win NSF and group grants and use NSF compute. There's two, one called Access, one called NAIR, with GPUs for the community use. So two examples of my own work on AI and data science. The first, as Edgar mentioned, is this vertical data science. I hope most people have heard different versions of this talk. It's really the practice of responsible data analysis, decision-making. I started on this path, first paper 2013 on stability. It's really try to respond to this reproducibility crisis. And the paper with my former student, Carl Kumbier, came up 4 years ago. It's really try to produce trustworthy data-driven result, which is very big part of AI, because data science big part of AI these days. And then really look at the whole pipeline. It's a philosophical conceptual framework, and it's evolving constantly. It's now really set in stone, and we need a documentation requirement. So it's predictability, computability, and stability. Right? Predictability has been generalized to unsupervised learning in the book, and also working on inference. And stability is a huge expansion of statistical variability to stability, including numerical stability. And you basically define it with a documentation that's appropriate perturbation or human judgment call you might make differently so that you ensure the stability. When you detect instability, you have to find ways to make it stable. It's a unification synthesis of statistics and machine learning ideas. So bring to AI, I just finished a short paper with my colleague Ahmed Alam from Berkeley, try to rethink about a vertical data science for medical foundation model. I work a lot on medical AI these days. I believe it's a low-hanging fruit, which we can make positive progress. And you can see that all the things in data science lifecycle has to be rethought. We don't have problem formulation when you do large language models. Which data use, we usually don't know. So there's this upstream and downstream separation. What's reality check unclear. So all this framework, all the things we used to kind of figure it out in the book now need to be rethought. So check out my website and also Google archive for the paper. So it's a really short paper. And then back to the book, right? The book became available online, read@book.com, free in February, and the hard copy you can purchase October 15th by MIT Press, actually in the machine learning theory. So definitely you can see that the machine learning people are pretty open-minded to include this in the machine learning theories. And this is the online version. You can see that you can click on the left and right. And the intended audience is for data scientists in statistics, and can be used, or parts of it can be used for statistics, machine learning, data science classes. I use it with David frameworks and elements of machine learning for the PhD level applied statistics machine learning class. You can take different chapters, have data cleaning chapter, problem formulation, and you can code, and the data sets are available. So another AI work we have done to my postdoc, Sophie Hauyu, actually was Arnaud's PhD student, and Nikhil Ghosh, who was my student, now just joined Flatiron Institute as a postdoc. Here, we're really looking at fine-tuning of large language models. So people know that like Meta, Llama is an open source model. And many people like in academia, in industry, take the open source models and do fine-tuning. You're hoping that the pre-trained models will learn certain representation relevant to you. And you have smaller data set, and you want to fine-tune for your purpose. So it's used a lot. And one method which has been very useful is called LoRa. Instead of updating the weights in the full model in all directions, you do B times A, which are both low rank matrices. And you up them in this low rank matrix direction and only fine-tune much fewer parameters. So our paper is really, this is the LoRa algorithm. So you have already W, which is already trained, pre-training took from Llama, and then you asking how can we update B and A. So what we did was really finding that it's not a good idea to use the same learning rate for both N and B, because the R, the low rank, is very different dimension than the A when you multiply the embedding, say when the width goes to infinity, and therefore they shouldn't be tuned with the same efficiency, same learning rate, and therefore we can speed things up and even gain some performance. You're on different paths. So since the paper was ICML 2024, two kind of engines already collected our LoRa Plus as one of them called the state-of-the-art efficient tuning methods, and recently Hugging Face also included as fine-tuning method. So what are the opportunities for statisticians? As I mentioned, safety of AI, software in medicine and science. I think there's this infinite width work, which we've been using for that LoRa Plus paper started by Greg Young and colleagues. It's really, I think, one of the very useful theories for deep learning, especially it's for optimization. Generalization is still unknown. And you can work on get efficient fine-tuning algorithms, as I showed you, and then you can work on trustworthy and certain quantification. How? I think we really need to engage, closely work with AI researchers in CS and domain scientists, or take a leap to industry lab. I personally don't think that we should play the role of police, but even we do want to play police role, if you do, we need the audience. You cannot be a police if nobody listens to you. So we need to get out and go to machine learning conferences and publish there and bring AI in. We have state journals and conferences make central AI research, but the key for our impact is software, software, and software. So how can we compete? I think we need to be relevant and engage. And after that, we should emphasize quality. If you cannot be relevant, engage, quality you don't even have the impact. So for me, it's really curiosity and desire to be useful professionally and responsibly help me to get into this different problem. Just like problem come with different shapes and colors, you go where the problems are, not what you think should be the problem. And I have pretty versatile experience in many different areas in theory, methodologies, here's a list, and in broad range of interdisciplinary research. That's what I bring to the table to do AI research. And I would encourage people to be prepared and take risks when opportunities arise and have fun. I like to work in cold areas and find a unique angle by understanding your own strengths and weakness and find talented collaborators. I have been lucky to have many talented collaborators, including postdocs and students, and cultivate a positive team culture so people can work in groups. And then we have a senior member of my group helping mentor students, younger students. As I said, right, review data science, I think provides a good angle. And the book itself took us 9 years. And we have many success stories for cancer detection, epistasis discovery, and we develop new methodologies too by adding stability to unstable algorithms for whatever the purpose you want to use. Again, the book, we got a very positive review recently by Yoel Benjamini in Harvard Data Science Review. And check it out, there's a free version. And I became a scientific advisor for Simons Institute for theory computing at UC Berkeley, and then there are 2 great programs going on. You can sign up to have the stream and watch videos. And so I highly encourage you to check the program out. We have one on large language model transformers and also modern paradigm in generalization. Thank you.
Thank you very much, Bin. This is very inspiring to see and a lot of insights there. And we will return to all of these issues to discuss them in more depth in the remainder of the webinar. Now I'd like to turn it over to Arnaud so that he can also give his own presentation and introduction. And let me first just briefly say a few words about him. So Arnaud Doucet is a professor of statistics at the University of Oxford, and he is also senior staff research scientist at Google DeepMind. His research interests span a wide range of areas, including computational statistics, machine learning, and Monte Carlo methods. He has also authored hundreds of papers. He's edited books, and he also has tens of thousands of citations. His work has been recognized by a number of awards, including the IMS Institute of Mathematical Statistics Medallion Lecturer in 2016, as well as the Guy Medal in Silver from the Royal Statistical Society in 2020. And he's also had extensive editorial service for the field, including leading journals like Annals of Statistics, GRSSB, and conferences as well. So we are extremely honored to have him alongside with Bin here. And I would like to hand it over to Arnaud so that he can talk about, discuss his presentation.
Yes.
Arnaud.
Yes, sure. So, I mean, I had first been asked to, present a few slides on my leadership journey. So the first slide are not going to be related directly, to my summer work in AI, but more about how I became, a leader, whatever this means, on, kind of my experience on what led me actually to a kind of position where I work between AI and ML. So my background is actually somewhat quite different from being you. So I'm from the French system. So in French, we have this very exotic academic system where usually after your high school, you don't go to university, but if you're a good student, you go to some kind of boot camp where you do intensive math and physics. And I was really keen to becoming a physicist, but like almost everybody, I eventually become an engineer. I went to one of those grandes écoles. So this background is actually quite interesting because this, what they call engineering school in France, is very still, we do a lot of maths, rigorous maths. And it's a mixture in the school I was, electrical engineering, information theory, computer science, and so on. So that's very interesting. In particular, I did a lot of control signal processing, measure theoretic proba, almost no statistics, unfortunately, but eventually I pick it up a bit later. So it's a good like internship, research internship. I did mine on neural network in 1992. I thought it was absolutely terrible, and I would never use that again. And eventually, I changed my mind later on, actually. But anyway, I ended up in 1997 with really a background, really signal processing. And in particular, I worked on, at the time, MCMC, but also what was not popular at the time, but became popular, which was this kind of particle method, like particle filters and so on and so forth. So in 1997, I was a very exotic research subject, but I focused on this type of things. Somehow coming from signal processing was very natural. And actually, the first application of those techniques were really not in statistics, but mostly robotics, computer vision on this type of application. It came later that econometrician and statistician adopted those techniques, but early on, that was not really the case. So eventually, because of this kind of background, I did a postdoc in Cambridge engineering department, and then I went through the world, explored various departments. So trying in the Tripoli department, then I was back to Cambridge as an assistant professor, and I moved to stats on CS, and eventually decided to focus on stats, actually. So that's what I did during the course of my career. So I've been pretty much all over the place. And the benefit of having done that, is that obviously I've come across different communities, and I had a kind of fairly wide background. It might not have been necessary to go all over the world to achieve this, but eventually that's what happened in my case. For various reasons I might explain later, so I was in Oxford Statistics Department. It's a very nice department. I was doing good work, having good student, but I felt I was focusing a lot on computational statistics. I felt that somehow, the kind of work I was doing was becoming more and more somehow irrelevant, in a sense that it was not really what was exciting people. It was, becoming diminishing returns. It's something that I got frustrated. Also, students, the best graduate students, they suddenly decided they didn't want to work on computational statistics anymore. They just wanted to do machine learning. Good example is Sufyan, the person who is now the postdoc of BNU. He's a very bright guy. He was supposed to do his PhD on MCMC, but he came, he said, come on, I'm not going to work on that. He's right, actually. He was very right. So I had to reorient my research because of the student, actually. Initially, I think there was a combination that was kind of a bit frustrated my own research, but also the student really pushed me somehow to kind of reinvent myself. And I was lucky enough that, I secured originally this kind of part-time appointment at DeepMind, and it has really, really been extremely fruitful, I think, in terms of new research direction. And has also kind of helped me solving actually the problem I was trying to solve for many years, but somehow I didn't have the tools. And by coming to machine learning, I was able to really actually develop new skill on really basically solve problems I was interested in. So I guess we'll come back to that. So in terms of leadership, I mean, I don't have nothing, really extraordinary. Some people lead big institutions, and they lead a lot of big, initiatives. I have to say, it's not. I'm someone who's been. I've been organizing a lot of workshops in my career from the very start. From the start, I was a postdoc. I really started organizing workshops everywhere I could. So that could be like, we had something early in Cambridge. I went to NeurIPS in 1999. It was a very small conference with about, 200 people in Denver. I had never heard of it, and it was quite interesting. I never expected I never foresee that it would become that big. Some are always having this kind of workshop with various, trying to have interdisciplinary event with people not only from my community stat, but having people from either at the time computational physics, chemistry, CS, engineering. And that was really something that actually really helped me to develop connection during the course of my career. And I've kept some of them, and it's been really, really helpful. I always tried to involve from the very start a large number of PhD and postdocs. I was myself a postdoc when I started to do this. And more recently, what I've been doing mostly in the UK is, you can call it, I wouldn't say necessarily leadership, but I've been trying to kind of convince people, particular from computational statistics, to embrace new subjects and to move away from the traditional MC and particle methods on which they've been working for many years. So it's perhaps you don't have this problem in the US, but I think the UK, that perhaps the community is a bit too homogeneous, working on a fairly similar topics. They're very good at it by trying to push people to explore new direction, especially because they've got the skills to do this. So I devoted a lot of time over the past 4 or 5 years doing this, actually. In terms of more general things, I was former chair of the Royal Statistical Society Research Committee, associate editor for various journal stats on ML Stats Conference, and advisory board for some research institute on review panel, trying also to talk to people either in government or obviously in research administration about the kind of challenge which are currently now brought by AI, actually. In terms of university, I will say my main contribution, obviously I've been training a lot of students now at this interface between stats and ML, but the main thing I've been trying to do is we had a center for doctoral training at the university, and we basically partnered with Imperial College to develop a novel training program, which is basically at the interface between statistics and machine learning. So the curriculum is like, I would say, the standard, I would say high-dimensional statistics, some causal inference, but we have also a course on reinforcement learning, a course on generative modeling, deep learning, and so on. And in particular, also what we've done, we have additional training for programming, because a lot of people that come in, they can be very good, theoretically, but have actually not necessarily the right programming skill. And this is really what we've been actually pushing. So having also internship in companies for people to develop those skills, actually. So that's been really one thing we've been pushing. It's been very, very successful, and it has attracted very good students as well. And in terms at DeepMind is a bit different in a sense, because it's not like I'm leading a big team. I'm with a small group. On some of my what I've brought, I think, DeepMind. So I'm not going to come and beat them at training their large neural network. This is obviously not where I have a competitive advantage. So a lot of things have been on trying to kind of in particular bringing a bit of statistics to DeepMind. We have really not many of us having a kind of statistic background. So having some reading group, statistics and certainly qualification, having giving lectures on the mathematics of generative modeling that go behind the algorithm, becoming some of the to-go person to answer stats question, this kind of thing. So this is essentially here trying to bring more some of the stats culture within this organization. So after that, many other things of a point. I mean, I could discuss some of the questions you ask. So I didn't prepare a slide for that, so yeah, I wrote the document actually. I don't know where it is, so I can start my slide anyway. This was
thank you. Thank you very much again. It was very inspiring, and these slides could be used for either. Originally, we thought them to be sort of introduction to your own path, but they can also be used to answer some other questions. And this is it has been very inspiring to hear both presentations. Both of you have really emphasized the importance of training. So students, undergraduate students, graduate students, they come in and they learn some skills, they take courses, and that's primarily what shapes their education in statistics. And I think if they see, that also defines what they think about as being statistics. Historically, I think statistics has been pretty successful in having some intellectual core. We have a set of kind of well-defined problems that we're looking at, and that kind of gives us something to identify ourselves. But things are developing, right? So I've already heard that learning more programming and learning about the entire life cycle of the sort of solving problems, from collecting data, processing it. Maybe if you could talk a little bit more and more specifically and more details about what's the right way to change our educational program, undergraduate level, master's level, graduate level, to make it modern, but also maybe not to like prematurely throw out some notion. Like maybe right now it's not, people don't talk about unbiased estimators that much, but it could be useful in 20 years. So how do we ensure that we basically keep our core intellectual? Yeah. So either of you, whoever would like to start first, and then yeah.
So maybe I can start, but obviously Binu made already very good points during a talk. So in terms, I think one of the main weakness, I see of like people go, with an undergraduate degree, at least in the UK, is that typically the programming skills are just not up to the right level. And in a sense, I think they really need to be like somehow we need to reinforce drastically, the programming component of those degrees. Also, when they tend to do programming, they work on, I mean, I don't know it is, in Wharton, but in Oxford, they tend to do R. R is a fantastic language for, some of data analysis, a massive, large amount of package. But when it comes to do like, produce some like, proper code, it's really not up to the level. It's really problematic. On some, I think I think the minimum would be like learning like language like Python, which are more widely used also in industry. But also it goes much further than that, because there's obviously a lot of places people learn Python, or they pick it up by themselves. But there's also all the kind of data management, parallelization, database, all these things is actually really important. Everything related directly to architecture. You can have algorithms which on paper are good, but in a sense, when you try to implement that on a GPU, it doesn't scale, for example, or try to do that at DeepMind on the TPU, and then suddenly your great algorithm become completely useless. So I think this is something that has really have to be part of the education. It's not easy because these things are this field is kind of moving very fast, but it's still, I think, something that has to be done. I mean, we did it quite successfully, I think, at the PhD level, at the undergraduate level. I think in Oxford we're not yet there. I think in terms of course, similarly, having introduction, I mean, obviously we shouldn't throw away, like obviously high-dimensional stats or empirical process. I mean, these are really important tools that people should be familiar, with. But I think really like starting to introduce course like learning theory, deep learning, so the element of deep learning, generative modeling, all these things can be done on I think it's like actually useful. I mean, it shouldn't be that you have students that finish an undergraduate degree who don't know. Students who don't know what generative modeling is, for example. It seems to me like completely a bit insane, actually. So yeah.
Thank you. Yeah, I will have some follow-up questions, but I would like to ask Bin if she has further things to add or elaborate.
Yeah, I want to resonate what Arnaud said, but just add a bit. So at Berkeley, I think two things I think we've done pretty well. One is I became our Berkeley Statistical Computing Facility Faculty Director. And one thing we did was, of course, a lot of my colleague Chris Patchwork's work. It's really have a boot camp on computing school when people write. So you kind of level the field. And then I also organize the different people teaching different computing. We have a class by Fernando and Philip Stark on reproducible research. And my class used all the computing, parallel computation. But I had used R until this semester. So what happens at my book is I'm doing a new master's class in the spring. To prepare for that, I want to do a lot of deep learning. I talked to former students who said, you have to do deep learning if people are going to find jobs. And since I got into deep learning with preparing that class, definitely Python, we made a choice moving to the computing class, Chris Patchwork, to Python. And then I moved my applied statistics and machine learning class to Python as well. It's just like if you want to work on deep learning, you cannot stay with R. It's not enough. So, and the other thing I point, like about 20 years ago, Berkeley Statistics already removed preliminary exams. The rationale was because we want students to come from CS. and they're just not as good with the math. And also in hindsight, the preliminary exam also defined the core to a lot of students because you drill them, they spend a whole summer on it. And our first year PhD student theoretical class, it just hasn't evolved. It's still what I learned when I was a graduate student. So that reinforces each other. So I would encourage colleagues across the country, across the world, consider not doing the traditional preliminary exams, maybe into oral to bring a little research into the fold instead of it's what you learned from the basic 2 layman books or variations on that. I think that has been a force that make us move slower because people define statistics, that's the core, that's what you drill on. And either we bring new material into the course. So 20 years ago, I taught the theoretical version. Like we have 2 classes, used to be estimation, point hypothesis in layman book. So when I taught you 24 years ago, I moved all the empirical process to the B part and put all the information used to be 2 span into A. And that Berkeley since then has been doing the more modern theoretical statistics in the B part, but a lot of places still more like a topic class. So I hope that happens. We have done that for 20-some years and worked out really well. And that's one change we can make and really embrace deep learning.
Some people would argue that if we are, in some areas of biostatistics or econometrics, the classical things are still very relevant. And so I wonder, what would you say to people who say, like, we still need to teach like the classical core material in quite a lot of depth? What's the right, yeah.
Well, I mean, we put 2 semesters of layman into one and worked, right? You have to make space for the new material. I'm not saying that the ideas are great, but you need to go through all the math, like for most powerful like tests, things like that. I don't think so, right? It just, you can still teach the ideas, but you don't have to do the math because the math is not as relevant as many years ago. And the field has to evolve. If we don't evolve, we don't have life.
Great, thank you very much. And it's very, very interesting to hear 2 different, yes, please.
I would want to emphasize that I think like statistics is really at the risk of basically in the next 20 years, in my opinion, to disappear. I don't say it's if basically we don't embrace basically, also the tools that have been developed originally outside our community. And there's nothing wrong with that. And statisticians can have a lot of things to contribute to them. But we shouldn't kind of like, I have colleagues, I'm not going to name them, who kind of refuse, to kind of like, admit there's a kind of like relevant work in like the community, like machine learning. It's ridiculous. Yeah, perhaps there's no proof for all the things they're doing, indeed, but they have great empirical results. If you have great empirical results, it's a source of inspiring problems. It shouldn't be seen as something like which is like, we should avoid. I mean, it's like if there's like repeated empirical, success, there's something behind, and we should, as a scientist, try to get an understanding of those things. I mean, not basically shy away from them.
I mean, that's really essence of statistics, right? We solve problems. Then we use mathematics as one possible tool to solve problems. There are also computational tools. I mean, we wrote a report 2019 with a bunch of people, Ximing He and David Madden. This is statistics at the crossroads. That's kind of saying gently what I'm now saying more bluntly, that we are in danger. We recommend people take a look. It didn't really bring a lot of attention to this problem. We're pretty blunt without saying exactly the words, saying that we're really not doing that well. But people, I think, I really encourage everybody to talk to other people, get their view of what they think about statistics. Talk to your colleague in chemistry, in physics, talk to your undergraduate students. Just get a view of what other people think of us. And that will help to be more realistic.
Great. Yeah, I put the link to the workshop report, Statistics at the Crossroads. Yeah, that's all very interesting. And like Arnaud said, probably just if you ask statisticians starting tomorrow, they will not be able to train a bigger GPT model than the computer scientists. So it's going to be a more gradual sort of change in the training. and it cannot be like completely abrupt. But I think both of you mentioned that we do have some sort of strength and some sort of areas where we can contribute something to a big team of big machine learning research group, for instance. So maybe could you potentially elaborate a little bit about what more detail about, let's say, related to uncertainty, how what can statistics contribute that maybe the machine learning community misses? And maybe Arnaud, I think, didn't have that much chance to talk about this, so maybe we can start with him. Yeah, what exactly can a statistician do that's valuable? Yeah.
So I mean, for in terms of like for example, uncertainty quantification, it is clear that tools like like conformal prediction, this type of tool, which are this kind of like essentially wrappers around a black box, are very powerful. I mean, so I've been working a bit on that. I mean, I'm far from being a specialist, not like you, Edgar. So I just like did a bit of application because I thought that was something good to kind of like demonstrate in DeepMind. That's like you can do this on so in most application, I should be mentioned, they don't care, because in most application, if it is like to predict a cat or a dog, whether you have high uncertainty, it doesn't really matter. But if you move obviously to health, for example, application, then you need to obviously to be much more careful on you need like obviously principle like theoretical guarantee. So this is where I think for example, if you are uncertain quantification, you want to kind of push something in this area. I think this type of application was to target. It's not as has been mentioning. It's not like super hot area. It's very important, or a bit cold. It's not overcrowded, and this is where you can play to your strength and bring this kind of tools, for example, to this type of domain. I mean, I've tried to do that. It's difficult. I found it very difficult because people don't have the vocabulary we're having, try to explain what's the prediction set, what kind of coverage, what does it mean really, or it's unconditional, conditional, and it's not kind of easy to explain. I mean, I attended a lot of meetings, people tell us, oh, our model is already calibrated, and then, everybody in the room has a different way of defining calibration. It's always empiric. So it's kind of really difficult to get this message across. But this is where I think people have really to really push for this interaction and try to kind of explain what those techniques are bringing. And I think in a lot of scenarios, they are really bringing something valuable. So there are a few people doing that. People I'm thinking on this uncertainty quantification. There's been a great work from Hashimoto in Stanford. I think is doing really good work trying to bring those tools to LLMs. There's much more to do around those lines, and you can do things with active learning or experimental design. There's a lot of things to do really in this which is really more statistical work than machine learning. And really, this is something. These are a lot of challenges to address here and to embrace. So really, I would work on, but I say you have to target the kind of like right application. If you go, I mean, a lot of application, for example, I found out later, people don't care about uncertainty quantification. They say they care, but actually, as long as they have some kind of error bar, whether it's obtained by any like heuristic or something, really heuristic, it doesn't really matter. But there are applications really like from health. Health is the big one, I think, where you can really make a difference and really strongly encourage people to work on this type of applications there.
Yeah, thank you for this. Yeah, conformal prediction is kind of one possible approach, and there's been more and more research. Interestingly, it was also not necessarily started by statisticians that much. Vladimir Vovk, one of the leading researchers, really a computer scientist, mathematician, and statisticians got into it a little bit later, and now I think there's more and more. Yeah, that's interesting. Yeah, so Bin, please.
Could I add something?
Yes, please.
So the uncertainty quantification, I think some people don't care, but statisticians feel like we know how to do it. But I want to challenge that too, because you look at the data science pipeline, there are two sources of uncertainty which we address in our book, chapter 13, which we don't take into account, which is data cleaning uncertainty and model choice uncertainty. So even there, I would like to think we have to enlarge the consideration of uncertainty. And things like from data cleaning, it's just practically very impactful. And it's not easy to think probabilistically. It's a lot of human judgment calls. So even we say we care uncertainty quantification, I like to make a difference. It's not like you can give some uncertainty. You need trustworthy and meaningful uncertainty quantification. That's much, much harder. And for whom? All those questions, I think we could embrace because we do feel like we own uncertainty. But look at the practice, there's a gap. The important source uncertainty we're not taking into account. That's what we try to address in the vertical data science. For conformal inference, actually, before Wolf wrote his paper, it's a method a lot of practitioners already use, especially in time series. You take the residual, you do some uncertainty there. It's good to give a name. So we have recently have an ongoing work compare our PCS uncertainty quantification with conformal. For low dimensional problem, we find that actually the PCS approach, I believe we should have diversity approaches, have shorter intervals. And also we have a subgroup adaptivity. So we should compare, right? That's how we compare with conformal inference.
Sure.
So we really need empirical evidence for the PCS inference and also for conformal inference. That's eventually going to be what matters. And there's a question about diversity approach. I think both Arnaud and I happen to work on deep learning because AI is about deep learning. I don't think we're saying that everybody should work on deep learning. It's just right now, we don't have enough people working on deep learning. And even you don't want to work in research for teaching, students will need at their job deep learning. So you still have to get down, just like not everybody use linear model for the research, but we still teach. So as statistician, as a group, you still to know something, at least teach students something so they can use that for their jobs. So definitely it's not like we're talking about everybody, just the proportion of people working on deep learning, it's compared with the size of the community, I think it's not enough. Arnaud can say what he thinks.
Yeah, there's very few people actually working on it. I mean, there's a lot of empirical, obviously, people in CS, a lot of clever ideas have been developed, but in terms of indeed the foundation, there's a very limited number of people doing interesting work in this area, that's for sure. That is for sure, actually. On coming back on the uncertainty, I would say something. So I've been working on this thing, conformal, but somehow then there's a problem where you want to deploy something in industry. Typically, there's terrible, covariate shift. It's very, very difficult actually to run that practically because the methods are not going to prove very robust actually when you deploy that in real time. So there's a lot of challenges actually when you get into the real world, especially with medical data, which are particularly also dirty or needs to be cleaned. There's a lot of pre-processing that has to be done. It's not pretty.
Yeah, actually, that's great, and thank you for bringing that up. So, roughly speaking, I think we talked about uncertainties and talk a little bit about do we all need to focus on deep learning? Not really. So, but maybe towards the end, either some closing thoughts or kind of some concrete problem challenges. I think you already mentioned, talked a lot about this, but like concrete, unexpected challenges in the real world that you've encountered by in this sort of using statistics or machine learning for real problems. These would be something interesting to talk about.
So maybe I can start with some closing thoughts. I mean, so yeah, I should repeat. Yeah, I don't expect, like Vince said. I mean, I don't say that everybody should work on deep learning or ML related things. I'm just saying that statisticians should be aware of those tools. It's not possible to have statistician. You can have statisticians who don't know what generative modeling is, don't know what a neural network is. It's just wrong. That shouldn't happen. So the culture in stats should be modified, changed a little bit in this respect. Actually, so that's the main thing. After that, I say closing thought. If you want to work, between this area, machine learning on stats, and I think it's a exciting area. It's wonderful. I would say you have to be. It's challenging because it's extremely crowded. There's a lot of people trying to do work in this area. So I would say that you really need to kind of consult with experts somehow to kind of identify right problems. It's going to be very difficult for an individual if not properly supervised, to identify by themselves, what is an important problem in this area, because the literature is huge. There's so many papers. I mean, for work, I work at the moment on diffusion model. I've been doing that for 4 years. It's just, there's been like 20,000 papers, I think, published in 4 years. So it's, very difficult to follow what's going on. If you come to as a PhD student, you think you're going to come up with new ideas, it's a bit risky, actually. So you should try to talk to specialists, talk to practitioners to identify what is the right problem, okay, what they care about as well. And there are something that, that need a technical solution or really a theoretical solution, or you can contribute. And finally, and it's been said also, play to your own strength. Don't try to become like, the kind of an expert at training deep networks. I mean, this is not typically, if you're doing a PhD in stat, this is not, you might be good at it, but this is not perhaps, what you should really work on, and really try to really exploit your strength. You might be very good at more theoretical thing, might be very good at more methodological concepts, these kind of things. Okay. So yeah, that's it.
Yeah, to add to that, I would think that adaptivity is very important, right? We live in a living environment, we have an ecosystem, and to see who are the users. Suppose we would produce a method, who are using and where they are going. I mean, that have to be taken into account seriously. And get out of your stat department, go to other departments' seminars. Often they are data-driven, scientists solving data problems. And just be aware how other in our environment, how people see us, whether we can make contributions. And what I find useful is, even in my group, we help each other read papers. So nobody can read for all the papers. So we basically group together and one person read a paper, share. And we really have to work as a team, both even understand what's out there, be informed, also in terms of getting results. So I have a ER medical AI project. I have also a national, like a cybersecurity project, just merge the two teams, just because we felt like we need to work together. And you have to be comfortable working with people. I go to assignments a lot because in Berkeley, and the young people there often in SGA, they just meet and they start working on problem together. For them, it's very natural. And I don't think we have quite a habit of doing that. And that social change is needed. And take some risks. It's okay to fail sometimes, especially if you're tenured.
Yes, very, very inspiring. Yeah, a lot of valuable thoughts in terms of teamwork and so on. I think we're running very close to the end. So one more question in the audience that I'd like to just mention. There was somebody who asked about curriculum proposals. I think, at the moment, probably there's no unified curriculum for what things should be updated. There's a group called Stats of AI that I've been part of. It's headed by Hongtu Zhu and Tian Zhang that have been trying to develop something. Maybe in some time we will have something. Well, thank you very much, everybody, for listening. Thank you so much, Arnaud and Bin, for being here, sharing your thoughts. Thank you as well to people behind the scenes, Megan, Glenn, Lauren Crawford, Jessica, Ginny Lee, Amita Manatunga, and stay tuned for more events like this one. Thank you so much.
Thank you.